So my dear students, this particular session is going to be the complete chemistry formula revision. It's going to be a very short and precise session, right? And this particular session will help you in order to memorize all the formulas which are involved in all the chapters of your chemistry. And you know, in your NEET examination, there are, more than like 4 to 5 questions, right, from your physical chemistry part, which are directly the formula based ones. So if you remember the formula, then only you can solve those questions. If you do not remember those formula, you cannot solve those questions. First of all, let's start with the mole concept. In the mole concept, how many ways do we have to calculate number of moles? You know, there are 3 ways by means of which we can calculate number of moles of a particular substance. The first formula is given mass of the substance in grams divided by molar mass of the substance. Given number of particles of the substance divided by Avogadro's number, that again gives me the moles. Given volume of the gas at STP divided by 22.4 liters. This is one more result by means of which we can calculate number of moles of a gas which will be present at STP, right? And if the condition is not STP, then we will have to use the ideal gas equation with the help of which you can calculate moles of the gas. N is equal to PV divided by RT. P stands for pressure of the gas, V stands for volume of the gas, T stands for temperature of the gas, right? Moving ahead. My dear students, there is one mole conversion diagram which you need to know. In order to calculate number of moles, either I should be given with mass of substance, or I should be given with volume of the substance, volume of the gas, or I should be given with the number of particles, right? You know, given mass of the substance divided by molar mass, that gives me moles, or number of moles of the substance multiplied by molar mass of the substance, that gives me the mass. Similarly, given number of particles divided by Avogadro's number, that gives me moles. Moles multiplied by Avogadro's number, that again gives me number of particles. Similarly, given volume of the gas in liters divided by 22.4 liters, that gives me moles. Moles multiplied by 22.4 liters, that gives me the volume of the gas. So with the help of this particular diagram, you can do some basic questions in which you can convert mass into volume, volume into particles, particles into mass, etc., right? Similarly, my dear students, over here, imagine that you have got 2 chemically non-reacting gases in the container. This is gas 1 and this is gas 2. I'm assuming that these gases are chemically non-reacting. If these gases are chemically non-reacting, that means these gases won't react to form any product. So these are non-reacting gases, right? So basically, I have got a gaseous mixture present in the container. Perfect. I've got a gaseous mixture present in the container. Now, my dear students, let me tell you, the mass of 1 mole of a gaseous mixture, you call that as average molar mass of the mixture, right? And how do you calculate that average molar mass of the mixture? That is mass of the mixture in grams divided by total moles present in the mixture. This is one result. Similarly, M1N1 plus M2N2 divided by N1 plus N2. What is this N1N2? N1N2 represents moles of each components over here. And M1, M2 represents the molar masses of these gases, right? Similarly, there is one more result with the help of which you can calculate the average molar mass. That is molar mass of gas 1 multiplied by mole fraction of gas 1 plus molar mass of gas 2 multiplied by mole fraction of gas 2. Similarly, my dear students, if this mixture will be present at constant pressure and temperature, at that point of time, this is the result with the help of which you can calculate the average molar mass of the mixture. So these are different ways with the help of which you can calculate average molar mass of the gaseous mixture, right? Then comes your vapor density. How do you define vapor density of a particular gas? Vapor density of the gas is defined as density of the gas divided by density of hydrogen gas, provided the gas and hydrogen, they are kept at same pressure and temperature. In the similar way, molar mass of the gas is equal to 2 times the vapor density of the gas. There are some questions in the empirical molecular formula wherein you'll be using this particular result. Now, similarly, if you apply this particular result to a gaseous mixture containing non-reacting gases, do remember vapor density of the gaseous mixture is always equal to average molar mass of the mixture divided by 2. This is one more result which you are going to remember over here. Okay, moving ahead. Percentage of an element in a given compound is equal to molar mass of the element multiplied by number of moles of the atoms, number of the moles of the atoms of the element in 1 mole of the compound divided by molar mass of the compound multiplied by 100. One simple result with the help of which you can calculate the percentage of an element in a given compound. In the similar way, percentage yield is always equal to experimental amount divided by expected amount multiplied by 100. Percentage purity of a compound in an impure sample, it's always equal to mass of pure compound in the impure sample divided by mass of impure sample multiplied by 100, right? All these topics I've taught you in detail in this particular channel only, right? Moving ahead, molecular formula and empirical formula. This is the result. Molecular formula is equal to empirical formula multiplied by N. What is N? N does not represent here the moles. N represents the ratio of molecular mass of the substance to that of empirical mass of the substance, right? Now comes to the concentration terms. You know, with the help of this 1, you represent solvent. With the help of this 2, you represent solute. W stands for mass, N stands for moles, E stands for equivalent mass, right? Now, weight by weight percentage of solute is always equal to mass of solute in grams divided by mass of solution in grams multiplied by 100. Weight by volume percentage of solute is equal to mass of solute in grams divided by volume of solution in ml multiplied by 100. Similarly, volume by volume percentage of solute is always equal to volume of solute in ml divided by volume of solution in ml multiplied by 100. These are some basic results. My dear students, there are a few more results which you need to know. Weight by volume percentage of solute, that's always equal to weight by weight percentage of solute multiplied by density of solution in grams per ml, right? Mole fraction of solute is equal to moles of solute divided by total moles present in the solution. Mole fraction of solvent is equal to moles of solvent divided by total moles present in the solution. In case of the binary solution, chi1 plus chi2, it's always equal to 1. When it comes to the molarity, number of moles of solute divided by volume of solution in liters, or mass of solute in grams multiplied by 1000, molar mass of solute, volume of solution in ml. Similarly, molarity is equal to 10 multiplied by density of solution, weight by weight percentage of solute divided by molar mass of solute. One more result. Molarity of the solution is equal to 10 multiplied by weight by volume percentage of solute divided by molar mass of solute. One more result to calculate molarity. Comes to the molality. Molality, number of moles of solute divided by mass of solvent in kg, or mass of solute in grams multiplied by 1000 divided by molar mass of solute multiplied by mass of solvent in grams, right? There is one more result which connects molality with molarity directly. Molality is equal to 1000 multiplied by molarity divided by 1000 multiplied by density of solution minus molarity multiplied by molar mass of solute. In the similar way, molality is equal to mole fraction of solute multiplied by 1000 divided by 1 minus mole fraction of solute, and this is molar mass of solvent. So these are some important results, right, from which directly formula-based questions can be asked. I believe it's clear. Coming to the chapter, or there is one more dilution formula, you know it, M1V1 is equal to M2V2, or mixing formula, molarity of the resulting solution is equal to M1V1 plus M2V2 divided by V1 plus V2, when you have got non-reacting solutions. Okay. Now, coming to the atomic structure. In the atomic structure, if I ask you, what is the energy carried by one photon? It's h nu or hc by lambda. What is the energy carried by n photons? It's n times h nu or n times hc by lambda. What is the combined value of H and C? It's 12400 electron volt angstroms. At that point of time, you will take lambda in angstroms. H multiplied by C value you can take as 1240 electron volt nanometer. At that point of time, lambda has to be taken in nanometer, right? And at the same time, you know, 1 electron volt is nothing but 1.6 into 10 raised power minus 19 joules. Okay. How do you calculate power of the source? It is energy emitted divided by time taken. Energy emitted will be nhc by lambda and divided by time. This n by t over here is something which you call as the rate of emission of photons. Rate of emission of photons. Now comes to the Einstein's photoelectric equation. Incident energy is equal to work function plus kinetic energy maximum of the photoelectron, right? Incident energy you can write as h nu is equal to h nu naught plus Ke max, or instead of h nu you can write hc by lambda. This will be hc by lambda naught. This is Ke max. Or you can write the same equation in terms of stopping potential as well. You can write instant energy is equal to work function plus EV naught, where V naught here is not the threshold frequency. V naught is the stopping potential here, right? Similarly, there are questions directly based on the formulas based on the Bohr's model. radius of the nth Bohr's orbit, right? This is how you compare the radius of two Bohr's orbits. Velocity of the electron in the nth Bohr's orbit. This is how you compare the velocities of two electrons moving in two different Bohr's orbits. Time period of electron, and this is how you compare the time period of two electrons. Perfect. By the way, n over here represents the shell number in which electron moves, and z represents the atomic number of that single electron species which we are talking about. Total energy possessed by the electron is equal to minus 13.6 z square by n square electron volts. Kinetic energy is plus of this. Potential energy is minus 27.2 z square by n square. Maximum number of spectral lines obtained when the electron makes a transition between two energy states. That's n2 minus n1 multiplied by n2 minus n1 plus 1 divided by 2, where n2 is the higher energy state, n1 is the lower energy state. How do you calculate the wavelength of the electromagnetic radiation which gets emitted or absorbed when the electron makes a transition between two energy states? 1 by lambda is equal to r z square, 1 upon n1 square minus 1 upon n2 square, where n1 is the lower energy state, n2 is the higher energy state. And let me tell you, 1 divided by r value, do remember it from now onwards, it's 911.5 angstroms, right? Perfect. Similarly, moving ahead. De Broglie's wavelength, lambda is equal to h upon p, right? Or p you can write as mv, or you can write p in terms of kinetic energy under root of 2m kinetic energy. Or if you have got the charged particle q, which is accelerated at a potential difference of v, how do you calculate this de Broglie's wavelength? Lambda is equal to h upon under root of 2mqv. And particularly for an electron, lambda is equal to 12.27 divided by under root of v. This result is for electron when the electron is accelerated at the potential difference of v. Okay. In case of Heisenberg's uncertainty principle, error in position multiplied by error in momentum, it has to be greater or equal to h upon 4 pi, or you can say delta x dot delta v is greater or equal to h upon 4 pi m. Okay. Similarly, how do we calculate the total number of nodes? N minus 1. How do we calculate angular nodes? The value of L, azimuthal contour number. Radial nodes, N minus L minus 1, right? Orbital angular momentum, under root of L into L plus 1 h upon 2 pi. What is L? L here represents what? It represents the azimuthal contour number. Total number of subshells in a given shell is equal to the value of N. N is the principal quantum number. Number of orbitals, maximum orbitals, which will be present in a particular shell, that's equal to N square. Similarly, maximum number of electrons that can be accommodated in a particular shell, that's equal to n square, right? Perfect. At the same time, guys, I'll be sharing the PDF of this particular session in my Telegram. And Telegram is Chemistry by Wassim Sir. Chemistry by Wassim Sir, right? On that particular Telegram channel, I'll be sharing the PDF of this particular session. Okay? All right. Then comes your thermodynamics. In thermodynamics, how do you calculate work? Work is equal to minus integral V1 to V2 P external dV. Now we have got two processes, one is reversible, one is irreversible. In case of reversible processes, external pressure and pressure of gas, they are almost equal. Therefore, this is the formula with the help of which you calculate the work done in case of reversible processes, and this is the formula with the help of which you calculate work done in irreversible processes, minus P external delta V. Now, there are a lot of questions in which you are supposed to calculate the amount of heat absorbed or released by the system. And there are many ways by means of which you can calculate heat absorbed or released by the system. Number one, Q is equal to C delta T, where C is the heat capacity, right, of the system. Q is equal to Ms delta T, where S is the specific heat capacity of the system. Q is equal to NCM delta T, where Cm is the molar heat capacity of the system, right? Now, at constant volume, this is how you calculate heat absorbed or released at constant volume. This is how you calculate heat absorbed or released by the system at constant pressure. Right? This is valid at constant volume, this is valid at constant pressure, right? Now, how do you calculate delta U for an ideal gas, right? Delta U is equal to NCV delta T, delta H is equal to NCP delta T. What is the relation between delta H, delta U? Delta H is equal to delta U plus delta of PV. At constant pressure, you use this particular result. Keeping constant volume, you use this particular result. If pressure as well as volume both will be changing, this is the result. For a particular reaction which is carried out at a particular temperature, delta H is equal to delta U plus delta NGRT, right? Similarly, in case of isothermal processes, temperature of the system is constant, right? And if the ideal gas undergoes isothermal process, it has to follow this equation, P1V1 is equal to P2V2. If the ideal gas undergoes isochoric process, volume constant, then it has to follow this particular equation, If the ideal gas undergoes isobaric process, right, it has to follow this particular equation. And similarly, in case of cyclic processes, change in the value of a state function, that's always 0. Therefore, delta U, delta H, delta G, they are all 0 when it comes to the cyclic processes. I mean, delta U net, delta H net, etc., etc. Moving ahead. As per first law of thermodynamics, you should know delta U is equal to Q plus W. Heat absorbed or released by the system at constant volume is always equal to delta U, right? And that delta U is equal to NCV delta T. Similarly, at constant pressure, it's equal to NCP delta T. A lot of questions are asked in which certain reactions are carried out in an open vessel. How do you calculate work done in them? W is equal to minus delta NGRT. What is delta Ng? Number of moles of gaseous products minus number of moles of gaseous reactants. Similarly, Cp minus Cv is equal to R for 1 mole of ideal gas. Cp minus Cv is equal to Nr for n moles of ideal gas. Gamma, Poisson's ratio, is equal to Cp by Cv, which is always greater than 1. And Cv is equal to R divided by gamma minus 1. If you have got a mixture of chemically non-reacting gases, how do we calculate Cv as well as Cp for that mixture? This is the result, N1Cv1 plus N2Cv2 divided by N1 plus N2. Same goes for this one, right? Cp mixture. Now, you have got two types of isothermal processes: reversible isothermal processes, irreversible isothermal processes. These are the results with the help of which you calculate work done in reversible isothermal, and these are the formulas with the help of which you can calculate work done in case of irreversible isothermal. Now, again, you have got two types of adiabatic processes, and these are the three results with the help of which you can calculate work done in reversible adiabatic. And these are the two results with the help of which you can calculate work done in irreversible adiabatic processes. One more type of question you would have seen, that is, how do we calculate the final temperature of the system? How do we calculate final temperature of the ideal gas, which undergoes either reversible adiabatic or irreversible adiabatic? When the ideal gas undergoes a reversible adiabatic process, this is the result with the help of which you calculate final temperature of the gas. This is the result with the help of which you calculate final temperature of the gas. When the same ideal gas undergoes irreversible adiabatic process, this is the result with the help of which you calculate final temperature T2 of the gas, right? When it comes to entropy, how do you calculate entropy change? In mathematical definition is integral of dq reversible upon T. But a question is not asked as per this particular formula. Question is asked as per this particular formula. When the ideal gas undergoes a thermodynamic process, how do we calculate entropy change of that ideal gas? This is the result, or this is the result which you can use, right? Similarly, delta G is equal to delta H minus T delta S. If entropy is the sole criteria of spontaneity, then for the process to be spontaneous, delta S total has to be greater than 0. That means delta S system plus delta S surrounding has to be greater than 0. If delta S total is less than 0, non-spontaneous. If Gibbs free energy is the criteria for spontaneity, at that point of time, I can say delta G for the system at constant pressure and temperature. It has to be negative, then only the process will be spontaneous. Similarly, if delta G for the system at constant pressure and temperature is greater than 0, we say the process non-spontaneous. I believe it's again clear to every one of you. Now, when it comes to the important results of equilibrium, first of all, how do you, if this is the reaction which is given to me, which is at equilibrium, this is how you write the Kc expression, this is how you write the Kp expression, where these terms are concentrations of reactants products at equilibrium raised par their stoichiometric coefficients. Kp expression will be, this is the expression where these are the partial pressures of reactant products raised par their own stoichiometric coefficients. Now, the point is, what is the relation between Kp and Kc? You should know it now. Kp is equal to Kc RT raised par delta N, right? Similarly, how do you calculate equilibrium constant? It is equal to rate constant of forward reaction divided by rate constant of backward reaction. Now, imagine this is a weak electrolyte. Imagine this is a weak electrolyte. How do you calculate ionization constant of the weak electrolyte, right? Which undergoes a dissociation like this. It is C alpha squared divided by 1 minus alpha. And if alpha is less than 0.05, this is the way by means of which you can calculate alpha at that time, right? Now, if that weak electrolyte is your weak acid or a weak base, then Ki is something which you call as Ka. Over here, Ki is something which you call as Kb. If your weak electrolyte is either weak acid or weak base, then in case of weak acid, Ki is Ka. In case of weak base, Ki is Kb. And these are the expressions with the help of which you can calculate Ki. And if alpha for them is less than 0.05, then this is the way with the help of which you can calculate alpha as well, right? Similarly, when you talk about pure water is also considered as a weak electrolyte, right? And here Kw, ionic product of water, is nothing but concentration of H positive multiplied by concentration of OH negative, and at 25 degrees centigrade, it is 10 raised power minus 14. Therefore, your result comes pH plus pOH is equal to 14. That is valid at 25 degrees centigrade. Now, if you have to calculate pH of any solution, what you need to do? You need to calculate the total H positive ion concentration in the solution. Take minus log of that. You'll be getting the pH of that solution. If somehow you're supposed to calculate pOH of the solution, what you are supposed to calculate? Get the OH negative concentration of the solution. Take minus log of that. Get the pOH. That's all, right? Now, when it comes to salt hydrolysis, you have got different types of salts. Salt of weak acid strong base, salt of strong acid weak base, salt of weak acid weak base, right? These are the three different types of salts which we have. First thing, how do we calculate hydrolysis constant? Hydrolysis constant for different types of salts are given to us. How do you calculate degree of hydrolysis? These are the results with the help of which you can calculate degree of hydrolysis of different types of salts as given over here. And these are the formulas with the help of which you can calculate pH over here, right? So any question from these formulas can come. Okay. Now, in case of acidic buffer, how do you calculate pH? pH is equal to pKa plus log of concentration of conjugate base divided by acid, or you can directly say concentration of salt divided by acid. Similarly, in case of basic buffer, this is the result with the help of which you can calculate pOH. Perfect. And similarly, whenever you have got a sparingly soluble salt, how do you calculate its solubility product? This is the way. If the solubility here is S, concentration of AY positive will be X times S, this will be Y times S, and KSP, solubility product, will be concentration of AY positive raised power X multiplied by concentration of BX negative raised power Y. This is the general expression with the help of which we calculate the solubility product, right? Now comes to your electrochemistry. Only few results we have. First thing you know, for an element, standard oxidation potential of an element is equal to minus times its standard reduction potential, right? How do you calculate standard EMF of the cell? E naught cell is equal to E naught cathode minus E naught anode, where E naught cathode as well as E naught anode, these are the SRP values of cathode and anode. Now, this is the Nernst equation which we use in the most of the questions. E cell is equal to E naught cell minus 0.0591 divided by N log of QC. Delta G for the cell is equal to minus NF E cell. Delta G naught for the cell is equal to minus NF E naught cell. When the cell is at equilibrium, this is the result which we use when the cell is at equilibrium. Now, as per Faraday's first law, mass of substance deposited or liberated at an electrode is equal to equivalent mass of the same substance multiplied by IT divided by 96500. What is I? The current which goes into the solution. T, the time duration in which current enters into the solution, divided by 96500. How do we get the moles of the substance deposited or liberated? I multiplied by T divided by N factor of the same substance which is being deposited or liberated, multiplied by what? 96500. As per Faraday's second law, right? What happens? When you have got two or more than two electrolytic cells connected in series containing different electrolytes, gram equivalents deposited or liberated at every electrode will be the same, right? Now, there are few terminologies which are related to conductance. One is your resistance, right? Resistance is what? Rho, L by A. Its units are ohm. When it comes to conductance, conductance is 1 by resistance, right? You call it as, its unit will be Simon. Conductivity, 1 by R into L by A, where L by A is called as cell constant, you know it. And the units of conductivity here will be Simon centimeter inverse. Molar conductivity is equal to kappa multiplied by 1000 by molarity if you are supposed to calculate it in Simon centimeter square per mole. Equivalent conductivity, kappa multiplied by 1000 by normality, Simon centimeter square per equivalent. Degree of dissociation of the weak electrolyte is equal to molar conductivity of the weak electrolyte at a given concentration divided by molar conductivity of the same weak electrolyte at infinite dilution. So these were few results which are related to your what? To your electrochemistry. Now, if you talk about your chemical kinetics, if you have got a balanced chemical equation, how do you calculate rate of disappearance of reactant? Minus change in the concentration of reactant by time taken. Rate of appearance of product plus change in the concentration of product divided by time taken. How do you write the rate exactly? It is rate with respect to A will be minus 1 by stoichiometry coefficient, change in the concentration of A divided by dt. Similarly, in terms of B, in terms of C, in terms of C, in terms of D. It is just the difference lies in the sign over here. When you calculate rate with the help of reactant, you have to start with minus sign. When you calculate rate with the from the product, you will be starting with the plus sign. That's all, right? Similarly, when it comes to rate law, how do you write rate law for this particular reaction? It's in balanced form. Rate is equal to rate constant, concentration of A raised power X, concentration of B raised power Y. How do you calculate X, Y? X and Y you calculate experimentally. X and Y you calculate experimentally. X is what you call as order with respect to A, Y is what you call as order with respect to B. And X plus Y over here is something which you call as the overall order of the reaction. In case of zero order reaction, this is how you write the rate law. This is how you write the integrated rate equation. AT is equal to A naught minus KT. Half-life in case of zero order reaction, A naught by 2K. Degree of dissociation in case of zero order reaction, AT by A naught. Completion time in case of zero order reaction is equal to A naught divided by K. Again, when it comes to the first order reaction, this is how you write the rate law. And these are the different formats of the integrated rate equations in case of the first order kinetics. You need to remember all of them. I have taught this in detail in the sessions if you remember. Perfect. Similarly, half-life in case of first order is 0.693 by K. Completion time is infinite. That means a first order reaction never undergoes 100% completion. Alpha is equal to 1 minus e raised power minus KT. Time taken to complete X% of the reaction. Similarly, time taken to complete 75% of the reaction. Time taken to complete 87.5% of the reaction. Time taken to complete 99% of the first order reaction. All these are important, which with the help of which you can solve questions in very lesser time. Then, rate constant is equal to A e raised power minus Ca by RT, your Arrhenius equation. And these are different formats of your Arrhenius equation. Perfect, right? Now, this is one more result. This is one more result which you need to know. When you change the temperature of the reaction, how many times the rate of reaction changes. Perfect. And your equation over here becomes R2 divided by R1 is equal to 2 raised power delta T, which is change in temperature, divided by 10. Perfect. Now comes the last thing. What is that? That is the solution chapter. In the solution chapter, the first formula comes from the Raoult's law, right? Partial vapor pressure is directly proportional to mole fraction in the solution phase. Perfect. Similarly, PB is equal to P naught B chi B. When you will be mixing two volatile liquids, this is how you will be calculating total vapor pressure of that particular solution which has formed when you have mixed two volatile liquids. When it comes to your relative lowering in vapor pressure, P naught A minus PS by P naught A is equal to chi B. This is one more result which you can use over here to solve the questions. Your elevation in boiling point, delta TB is equal to Kb multiplied by molality, where Kb is what you call as molar elevation constant, whose value is RT naught square divided by 1000 LV, where LV over here is the latent heat of vaporization, and T naught is something which you call as boiling point of solvent here. Depression in freezing point is equal to Kf multiplied by M. Pi, your osmotic pressure, is nothing but CRT, where C is the concentration or molarity of the solution, right? Similarly, how do you calculate the Van 't Hoff factor? Right, for that electrolyte which undergoes dissociation, this is the formula 1 plus n minus 1 alpha. How do you calculate Van 't Hoff factor for this electrolyte which undergoes association? 1 plus 1 by n minus 1 alpha. And for a non-electrolyte, what is the value of alpha? Alpha value is 1. So these are the only formulas from which the questions will be asked, nothing else. So please and please do remember them. Right? I am telling you 4 to 5 questions will be directly formula based. If you remember these formulas, you can solve those questions. If you do not remember these formulas, you are done. Okay? So with this, I'll be taking a leave. Take care. God bless you all and love you all, guys. Bye-bye.